Okay, so very good morning and quick review of what we were doing in the last class. So we started the discussion on virtual work. Virtual work is a concept given by a mathematician, Bernoulli, Jean Bernoulli, in 18th century. And the idea of this method is particularly virtual work is, things are still stationary, but we assume some virtual displacements, but these displacements have to be, they should respect the constraints of the problem. And when we give such arbitrary imaginary displacements, the so-called imaginary work done should balance out, right? That's the idea. So whatever external forces are there, the net virtual work should be equal to 0. And when we write such an equation, that imaginary displacement that we have assumed, it cancels out, and what we are left with is a relationship between force or forces and moments and so on. So that is the idea of this method of virtual work in a nutshell. And as we saw in the last class, it's a very it's a quick way to get relationship between the cause and the effect. And the advantage, the particularly, we don't have to calculate the internal forces, we don't have to calculate reactions, isolating bodies and so on. So, so these are some of the advantages. One of the key thing in this method is the geometric relationship. So it is very important to get an idea, or particularly for if you want to solve a problem using virtual work, it's very important. And if we are able to see a geometric relationship between the input and the output displacements, so that is very important. We saw this example in the last class and using different methods. And yeah, this is what we saw in the last class. And now let me share this same example, but with a little bit more, by introducing a friction as well. So let me share this screen. Okay, so I hope you can see this writing application here. And we will now consider the same example, what we saw in the last class, but with friction. So now we have got some force here, Q. But now let us say the bottom surface has got friction. So if the bottom surface has got friction, so there will also be a friction force F, and there will be a normal reaction N. And here, of course, there will be a reaction R, and there is a load P acting downward. Right. So this is the same, stone crushing machine or mechanism that we have seen in the last class, but now we are considering it with friction. So this is the extra force small f, and now we are assuming that it is on the verge of sliding, right? So we want to calculate the maximum load P for which it is just about to slide. So in that case, your F will be equal to mu times the normal reaction N. And if you see the geometry, this is L, and this angle was theta. And we have to calculate the normal reaction N. And to calculate normal reaction N, we will do a moment balance about the point, let's say A, about point A. And if we balance the moment about point A, what we will get is P times L sine theta should be equal to norm N times 2L sine theta. And therefore, what you will get is P is equal to 2 times N, or in other words, the normal reaction will be equal to your P by 2. And so that is just one relationship to get the normal reaction. And once normal reaction is known, the friction force F is equal to mu times N, and that we know. Now writing the the virtual work equation. So now here comes the interesting part. So now this is an angle theta, and now we give a very small displacement, again imaginary displacement. We assume that there is an imaginary displacement by delta theta, and this point moves to something like this. So now we are giving it a small displacement delta theta. Okay. Now if this moves by delta theta somewhere here, this will somewhere here, a very good diagram. Like this. So this is going to be the new configuration, and let's name this as B and C. So by giving a virtual displacement delta theta, point C has moved to the new orange configuration, and similarly point B has moved to this new configuration here. And now we have to write the virtual work equation. So the reactions R is not going to do any work. P is going to do a work here, and this I can write P times delta YC, and delta YC is assumed positive upward, so P is downward, so we'll put a negative sign here. Similarly, XB is positive here, so our positive convention is this is positive X, this is positive Y. So the displacement of point B is positive in the right direction. Q is acting in the negative direction, negative X direction. So again, there will be a minus Q times the virtual displacement of point B. Same thing with friction force. It is acting in the negative direction and our displacements are positive. So this is acting like this, and this should be equal to 0. So in the last class, we have seen the first two terms. Now with the introduction of friction, friction is also going to do a virtual work, and it is given by this third expression that you can see here. So now the things are quite similar. So we will substitute.
Sir, how did you say that point C moved downward?
Point C moved downward. Well, you can visualize that if this delta theta is in this direction, this has to go down, right? So it has to come a little bit downward because we are rotating.
Then work must be positive, right, sir? P is downward and C is downward.
Can you repeat?
Work done at by P must be positive because that point C moved downward and P is also downward.
Okay, so thanks for mentioning this clarification. So we are assuming that delta Y is positive upward. So we are not considering whether it is moving downward or moving upward. So it's good you pointed out. So we are not considering that whether delta YC is positive or negative. It will automatically turn up in calculation, but P is in negative direction. P is in negative direction, and this we are assuming to be positive. So therefore, there is a negative sign here. Is that clear?
Yes, sir.
Okay, thank you. So this is the the expression for virtual work that we have written. Now we have to find the geometric relationship for delta yc, delta xb, right? In terms of the parameter that we have assumed is theta. So we are giving delta theta. And same thing, if you see in the last class, we said that yc was L cos theta, right? So that is the vertical position of yc. So from here, we will get your variation in yc, or virtual displacement of yc is equal to minus L sine theta delta theta. And similarly, your xb was 2L sine theta, and from here you will get delta xb is 2L cos theta delta theta. So when we substitute this expression here, we will get, so if you substitute this expression here, we will get q is equal to p by 2 tan theta, which is what we got last time, but now we'll have tan theta minus mu. Right? So if you substitute here and simplify it, this is the expression that we are going to get. So, so that is how we include friction in doing virtual work calculation. And again, delta theta will get cancelled out from everywhere and you'll get this expression. But now here, another thing that we can calculate is what is called as a mechanical efficiency of the system. So as you know, efficiency is output divided by input. So here we are basically concerned with the output work, and to be more specific, output virtual work divided by input virtual work. Because again, things are stationary, they are not moving, but in terms of virtual work, we can do this calculation. And so in this case, the output work, the output is on the load or the stone, whatever we are placing here, and therefore the output force Q is doing the work. So in the present example, if for the same example, if I want to calculate the efficiency, I can say this as Q times delta XB. Was it B? Yeah. Q times delta XB was the output virtual work, and the input is P times delta YC. P times delta YC. So that was your input work. So if I simplify it, it is 2L cos theta delta theta divided by PL sine theta delta theta. And that's the expression. And again, you can see here that this cancels. Now, if there was no friction, right, if mu was 0, then you will see that if I substitute the old value of Q, this will turn out to be 1. And this will be the same. But now if I substitute the value with the friction, the Q in terms of friction, this is 2 times P by 2 cancels. And what you are, if you simplify this expression, I'll directly write the final expression. It is 1 minus mu cot of theta. So your efficiency is, it turns out to be an expression something like this. And you can see that it is a function of mu and it is a function of theta. So if mu was 0, then it's 100% efficient. Whatever work is given, it will be transmitted completely. If there is some friction, then that some energy will be lost in friction and your efficiency will be less than 1. Okay, so I think that's about the example that we were discussing. Now let's move to the next example. So let us, another common examples which we will try to attempt is a figure something like this. right? So if you can see this figure here, someone is, Shalu, can you mute yourself? Yes. So this is typical examples that you can solve it by the help of virtual work, and we will see this is what type of example that we are going to see here. So these are like platforms for lifting things, and these are also some similar. I don't know if you have played with some toys. Shalu, can you mute yourself? There's some disturbance here. Okay. So yeah, so this is the example that we will try to discuss. Now let us consider this example where I have these. Okay, so the question is, what should be the moment m? Find m to so that the system is in equilibrium. Right. So you can imagine this system. So these are all pin joints which can freely rotate, and there is no friction in this system. And this pin here, so let's say this is pin A. This pin A can freely move in this slot, right? So this is a frictionless slot. And inside this slot, this pin A can freely move horizontally. Pin, now this is pin B, C, D, E, and F. So all these pins are frictionless, and they are pin joints. They can freely rotate. So we have to find moment capital M such that it balances the weight mg. Right? That's the question. Because so mg is the only force that is acting external to this system. So that is the objective. So now you can see that with so many rigid bodies connected together, now if we were to use the traditional force approach, it is going to be a bit tedious. And if you have a problem which is something like more of a zigzag, something like this, right? If you have got so many rigid bodies put together, it's going to be really complicated. So now here that's part of the answer to one of the questions in the last class, why we are using virtual work method. Now in the system, let us say if we give a virtual displacement to this theta. So our input is moment m, and let's say if I give a virtual displacement here, and it goes to a configuration something like this. Okay, again, it requires some visualization to visualize that. But if I give, so currently, let's say it has got an angle theta, And now if I give a small virtual displacement delta theta to BF, then the system will deform in some orange color configuration here. Now we have only two external forces. One is moment and another is the weight mg. So we'll say the virtual work by all forces should be equal to 0. So that is the principle of virtual work. And the first one is m times delta theta. That is, we can write very directly. Plus the second virtual work is mg times the displacement delta xd. And let us say we are assuming this direction as positive. So mg's direction we have assumed positive, and the displacement delta xd is in the same positive direction. So it's written like this. Now, so this is quite straightforward to write, but now we have to find a relationship between theta and xd. And if you see these link lengths, so these link lengths are all equal to L. I forgot to mention that. So these link lengths are all equal to L. So if this is equal to L, I can write the position of point D as this is L cos theta is the vertical component of FC. Then I can write vertical component of CB as again L cos theta. And again for BD, it is again going to be L cos theta. And therefore this is equal to 3L cos theta. And now if I take a differential of this, then this is going to be 3L times minus sine theta delta theta. And that's the expression. And now if we substitute this expression here, we will get the moment is equal to 3 mg times L times sine theta. So just by a very short this thing, we can get your final expression as this thing, right? Okay. Now, are there any questions? Or maybe let me complete the lecture and then we can have questions. Now here we have written this expression as m times delta theta. So I'm writing delta u is equal to 0, and what we have written this as m times delta theta plus mg times delta x. This is equal to 0. That's what we have written. And what is this? This is basically your virtual work by gravity. Virtual work done by gravity. Let us it's written like this. Now, if I take this term on the other side of equality, so if I take it on the other side of equality, it will be so this is virtual work by external forces is equal to minus of the virtual work by gravity, right? And this negative of work done by gravity, we are now calling this as potential. So we'll call this as delta V. So now here we are introducing, or I'm introducing another term which is called as potential or potential energy. So this is your virtual change in potential energy. So now what we can do is, instead of writing the virtual work done by gravity, or later on we will also include springs also into the system. So let me write it down. Instead of writing virtual work by gravity or springs, we will write the change in potential energy and this is going to be on the right hand side of the equation. So now we can say that the principle of virtual work can be restated in particularly when we have springs and gravity acting on the system. So I'll just write it down. The virtual work done by all external forces on mechanical system is equal to mechanical system in equilibrium. What to mention that? On mechanical system in equilibrium equals the corresponding change equals the corresponding change in elastic and gravitational potential energy of system for all admissible virtual displacements. Okay, so it may be a little confusing, but the idea is that we are going to write, so if you express mathematically it means that virtual work done by all external forces is equal to the change in the potential energy of the system. So this includes your elastic potential energy, and it also includes your gravitational potential energy. So if you have got springs, you have this term half kx square, and if you have gravity, then you have your mgx or mgh type of terms coming up here. So that is the that is the modified statement of virtual work. So previously we had everything on the left hand side, and that was equal to 0, but now we have brought some terms, work done by the spring and work done by the gravitational force. We are calling this as negative of potential, and then we bring it on the right hand side, so it becomes positive, and that's the expression for the virtual work that we have written. Okay, so now let us quickly derive the expression of potential energy for spring. So this is the first time we are introducing elastic element, and we introduce these elasticity by this springs, right? We represent it something like this. So let's say if this is the spring, and if we apply a force F, So currently it is unstretched, and there is, so we are applying force very, very slowly. And after applying the force F, it gets, let's say, compressed and becomes something like this. So F is increased gradually, right? So we are gradually increasing the F, and there is a Hooke's law for spring. Which approximates the spring force, and that is F is equal to kx, the famous equation. And from here we can calculate the work done. So the work done is your F multiplied by dx integral, right? So F is slowly increasing, and in making a small displacement delta x, the work done is F dot dx. Now if we integrate the total work done, F is your kx, so it is kx dx integral, so it is integral of kx dx. And let's say integrate it from the unstretched length 0 to of some stretched length, let's say x, and this is your half kx square. So this is the this is work done on spring. And now if you can see the work done on the system, or which is work done by the spring, it is going to be negative of it. And therefore, when for a system, when we write the potential energy of the spring is going to be your same expression, half kx square. And so that's your elastic potential energy of a spring when it goes from unstretched length to let's say a compression of x. But now if I have got a change in length from, let's say, x1 to x2, then the change in potential energy is going to be half k, the final displacement square, minus half k x1 square, right? So that is the expression for your any change from x1 to x2. And likewise, there is a term called as torsional spring. So if you have so these kind of springs are there in your auto closing doors and these things. So these are some examples of torsional springs, or you can even have a simple rod which twist it and it so the idea is you apply a torque, or if you apply a moment m, and that moment m is proportional to the angular theta rotation. So it is related to k times theta, but this is your torsional stiffness. So it is exactly parallel to the linear case. And again, if I do m dot d theta integral, so your elastic potential energy for the torsional spring is going to be same expression, half k times theta square. It's like half kx square was for linear case. This time this half k is the torsional stiffness now, times theta square. So I think that these are some of the basic concepts which we are going to use in the next class. I think that's all for today. We'll stop here.